All right, we are back. This is Calculus 1. We're looking at 4.6, limits at infinity and asymptotes. Oh boy. So let's get a move on here. We're looking at the inverse tangent, the arctangent. So f of x equals the arctangent of x. And they built on page 22, or on page 22 of the note packet, chapter 4. And they built a little bit of a chart. They didn't really go large for infinity. For x going to infinity and going to negative infinity, they should have, went 50, 100, 1,000. And instead they kept it pretty small here. So anyway, let's take a look at what it is approaching. So as x goes to infinity, as this gets infinitely large, that would be from, if you kind of mark it at 0, where it goes from negative 0.06 to positive 0.433, that's where the y goes from negative to 0. So if you go from 0.40, whatever that is, 8, down, that's like approaching positive infinity. And so as x, goes to 12, to 13, it's going to about 1.5, it looks like. And then as it goes up, that's going to negative infinity. So this way, there is an asymptote right there, and there is an asymptote right here. And it's going, the limit as x approaches infinity of f of x is actually equal to pi over 2. And now the reason I know it's pi over 2, it's 90 degrees. If you actually take pi, 3.14, and divide it by 2, you get 1.571. So about 1.6. So that's how we know, look, it's going down. It's 1.5 right now, but it stopped at 13. If we went, 15, 16, 20, 25, 30, it would close in on 1.57. So that is pi over 2. The reason we know it's pi over 2 is because this is the arctangent, and the normal tangent curve, if you think about the normal tangent curve, that is between pi over 2 is an asymptote, and negative pi over 2 is an asymptote. And so if you do the inverse of that, we're kind of flipping it and reversing it. Or I guess if we just twisted it this way, right? If we took it and rotated it that way, we'd have 90 on top, negative 90 on the bottom. This is pi over 2. This is negative pi over 2. And there's our curve. That is the arctangent. And so the limit as x approaches negative infinity of f of x is equal to negative pi over 2. So that's A and B. On the next picture, they have 1 plus 1 over x, and then raised to the x power. And that will actually approach E. 2.71, the natural log E. So that's what's going on here. This is 2.71, that is E. And that has the same, they kind of wrote it for us, so there wasn't much. E is approximately 2.718. And so this is just below 3. There's 3. And so 2.718. But they're saying this one, the right and the left limit are the same. So going positive infinity and going to negative infinity, they're both approaching E. Just this is approaching it from above and that from below. Where here, these are actually approaching different from the left side and the right side limits. So the first one is different from left side and the right side. Limits. Okie dokie. Lovely. Let's look at page 23. Oh, that's just a lot of pictures. So, yeah, about the only thing we'll add on in the middle of the, right under horizontal asymptote, that's usually ha, H-A. Oh, I uploaded 4.5 video and I did make a small error on the board. You probably caught it, or maybe it didn't. The mean value theorem. I said MVT, but I wrote MTV. I apparently had music television on the mind. Going back to the 80s or 90s. That was probably the last time I watched MTV. So this one, horizontal asymptote. Ha! So we just see ha, or H period, A period. That's fine. Either way, whether you have the periods or not. I'll know you meant horizontal asymptote, so you don't have to write it all out. We do a lot of writing in here, so anytime we can save some room like that, that's fine. On the bottom, on the very bottom of the page, those little E's, those are called an epsilon band. Then the limit is like L. So what's happening is, we've got this picture, but it's kind of closing in on this. And so we've got these little epsilons, but those can change. Like we can do a smaller epsilon band. And so those are little E's right there. And so it's called an epsilon band. And then the limit is L. It's an actual number, L. All right. Yeah, I'm gonna turn that off before it starts. All right. So that is where the limit of f of x is equal to L. So the statement, the limit as x approaches infinity, f of x equals L, means that for each epsilon greater than 0, there exists an m greater than 0 such that x is greater than m. So okay. So yeah, you can, m is just the, like, so if this epsilon band, we have an m going down here, then there's going to be another, like a smaller m there, or a larger m. This m is actually going to be larger because the epsilon band is getting smaller. So that's what they're trying to say there. Whenever x is greater than m. All right. Okay, on to page 24. So although this is rare, a function can cross a horizontal asymptote an unlimited number of times. Notice that the function below gets closer and closer and closer to the limit. And so that's what's kind of going on here too. It keeps crossing what it's approaching. All right. So let's take a look at 24. What three things? When we take the limit as x goes to infinity or x goes to negative infinity, there are three possible outcomes. Let's take a look. Number one, we will get positive infinity or negative infinity if there is no horizontal asymptote. Number two, we will get 0 if there is a horizontal asymptote at y equals 0. or 3, we will get a number L if there is a horizontal asymptote at y equals M. So those are the 3 scenarios. Limits of polynomials. To take the limit as x approaches positive or negative infinity of a polynomial, we only take the limit of the highest degree term. Okay, so that, yeah, you kind of look at the big dog. You want the big picture thinking. Like, what is going to have the most impact on y? So if I am looking at this, the highest power term, is what we're interested in. And so really, I'm only really interested in this one. So I want to look at the limit as x approaches positive infinity of just 4x to the 5th. These, think about the big picture. The big picture, I'm putting in 100 and then 1,000, then 10,000, and then 1,000,000 and 1,000,000,000. All right? What's that minus 9 going to do to that? That's not even going to be a blip right? That's going to have no effect. And so it's like, you know, if you take somebody that's worth $200 billion and you say, ooh, you just got a $10 fine for throwing that trash on the ground. It's not really going to dent their net worth at all, you know? And so, yes, minus 4x to the 4th would have more of an effect, but in the long run, not. You know, as I go billion, trillion, quadrillion, this is going to eventually look like nothing also. So we just kind of focus on that. That's the big picture. That's where it's going. So we're sort of thinking, all right, well, then that's 4 times some large number. We're just putting infinity there. You can't really take infinity to the 5th power. But now we can just look at that and go, what's going to happen here? Well, it's 4 times some tremendously big number to the 5th power. That is going to be a different tremendously big number. Positive infinity, or just infinity is fine. So then what if we have the limit as x approaches negative infinity of 4x to the 5th minus 4x to the 4th plus 2x minus 9? Well, again, we're going to do the limit as x approaches negative infinity, but we're only interested in the 4x to the 5th. So 4 negative super large number to the 5th power. So now you gotta use your brain here, because negative 1,000,000 times itself 5 times is going to be some huge negative number. And that huge negative number times 4 is going to be a negative infinity. And so you have to pay attention to what's going on with the powers. If that was to the 4th power, both of them would have been going to positive infinity. It wouldn't have affected that. But this would have been changed to a positive huge number times 4. And so even powered things there equate to positives, all right? And so, yeah, if we looked at the actual graph here, what's going on here? As I go this way, it's going down. As I go this way, it's going up. And then a bunch of junk could happen in between that we're not worried about. We're just worried about the end behavior. What's going on as it gets infinitely large? What's going on as it gets infinitely small? And that's going up, 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 and that's going down, down, down. All right, so let's take a look at the limit as x approaches infinity of 1 over x. Oh, yeah, that's always 0. That's, I think, what they're trying to tell us here. What's going on here? C over x to some power is always equal to 0. The second limit to valid only if f prime is defined when x is less than 0. And then the limit of e to the x is as it goes to negative infinity is going to be 0, because that's like 1 over e to the x. And so that's going to 0. So basically, if you take 1 divided by a really large number, you get something really close to 0. It approaches 0. It won't actually ever be 0. You can't take something to a power and get 0 out. You can get it really close. You can say 1 over 10 trillion. And, you know, in our real world, we would say that's 0.00000000000000001. And that would be, you know, for our purposes, 0. But it's not really mathematically 0. So the limit as x approaches infinity of 1 over x, that's equals 0. Because think of it, if I just did like, okay, x is 100, x is 10,000, x is 1 million. What's happening? That's 1 over 100, 0.01, 1 over 10,000, 0.0001, 1 over a million. How many? 3, 6, 2, 3, 4, 5, 6. And then the 1, right? 1, 2, 3, 4, 5, 6, 7. Oh, yeah, because the place is 7 and then the 1. Alrighty. So anytime you take a constant divided by, that's very important. You get this burned into your brain. That some constant, any constant, divided by infinity is going to go to 0. All right, as the denominator gets very large, the numerator stays the same. The value of the fraction as a whole goes to 0. All right, so numerator remains constant, and denominator gets infinitely large. The end result is the fraction as a whole goes to 0. Okie dokie, Chucky. Oh, I didn't do 1 over 10, 1 over 100. 2 places, 1 over 1, 2, 3, 4 places. Right. Oh, this should be, sorry. 1, 2, 3, 4, 5, 6. How many places did I have there? Just 1 million? All right, so 1 million, that should just be 1, 2, 3, 4, 5, 6. We should always be able to read this aloud. So this is 1 millionth. This is tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths. So there should only be 5 zeros there. Point, and then 5 zeros, and then a 1. Still really close to 0. But I've got to either add zeros or kill zeros here. 1, 2, 3, 4, 5. Okay. I didn't think that looked right. Let's look at 25 and 26. All right, so the limit as x approaches positive infinity. A lot of times, if it's positive infinity, you can just say infinity. 5x minus 8 over 3x plus 1. So again, we want to do big picture thinking, and here is the trick to do this, to find the horizontal asymptote. And there's a couple of ways you can do it, but on the test, you're going to have to show me work. So I'm going to have to see the work. But if you notice that the degrees are the same, the top dog here is 1 and the top dog here is 1, that's basically all it's going to be. It's going to end up being 5/3. And so, but I want to see this work, because when it's more complicated, you can't just do that all the time. And so this is what I want you to do. Basically, you divide every term by the largest variable in the denominator. So we don't really care about the numerator. You just look in the denominator. There's an x and there's nothing. So we're going to divide everything by x. All right? Then you simplify it. Then you do the limit. And I'm fine if you don't write the limit every time, but when you're actually executing the limit, you should say the limit. The limit as x approaches infinity of these x's cancel, those x's cancel. We have 5 minus 8 over x over 3 plus 1 over x. And now what you can do is we're thinking of it as 100 and 1,000,000 and 1,000,000,000 and 1,000,000,000,000. And so you have 8 over 1,000,000,000, that's 0. So the way we note that, you just put a little arrow through it like that and say 0, a little arrow through it like that and say 0. So those are zeroed out. So we end up with just 5/3. And now we can make our horizontal asymptote at y equals 5/3. Again, don't just say 5/3. We need the x's, we need the y's, you need to be precise. So y equals, that is a horizontal asymptote at 5/3. Again, if we went back to the original and you said, okay, I put in 100, and that was 500 over 300 basically. And then I put in 1,000, that was 5,000 over 3,000. The plus 1 didn't change it much. The minus 8 didn't do much. Those are going to 0 in the long run. All right? So kind of big picture thinking all of these things. All right, let's look at number 6. We've got the limit as x approaches infinity of 2x cubed plus 5x plus 3 over 7x to the 4th plus 3x to the 3rd plus 8x squared minus 13. And again, you're going to learn that when we've got a higher degree in the denominator than we do in the numerator, the overall end game is going to be 0. It's going to go to 0. And you'll see why. And I don't want you to just put 0 though. Don't just say, oh, I know that's 0, because that's a 4 and that's a 3. I want to see the work here. So what we're going to do is, here, this will save a little step. Divide everything by the biggest thing in the denominator. So x to the 4th, x to the 4th, x to the 4th, x to the 4th. Everybody gets an x to the 4th. X to the 4th, x to the 4th. All right? So we squeezed in an x to the 4th everywhere, and now we're going to do the limit as x approaches infinity of 2 over x plus 5 over x cubed plus 3 over x to the 4th over 7 plus 3 over x plus 8 over x squared minus 13 over x to the 4th. So now, if you thought 3 over x went to 0 quickly, 8 over x squared goes even faster. So this goes to 0, 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 this goes to 0. That's kind of the key here. So at the end of the day, we end up with 0 over 7, which is 0. And so the limit as x approaches infinity of f of x is 0 in this case. So there is a horizontal asymptote at y equals 0. All right. Okay, the limit as x approaches infinity of 3x to the third minus 2x squared plus 4 over 1 minus 3x. Again, we're going to divide everything by the largest power in the denominator, not the numerator, in the denominator. So everybody's going to be divided by x. And then we're going to take a look and see what happens. So we have the limit as x approaches infinity of 3x squared minus 2x plus 4 over x over 1 over x minus 3. And so when we look at that, this goes to 0 and this goes to 0. But basically, that's going to infinity. That's like 3 times, if we just look at the big dog, 3 times infinity squared, right? We would really just be looking at this as our limit after everything is said and done. Just that. Because that's just negative 3 on the bottom, so we don't really care about that. So we're just looking at this, and that is like 3 times infinity squared. You can't really do infinity, but large number. And so that is equal to infinity. So there is no horizontal asymptote. That's just going infinitely large. As x gets infinitely large, y gets infinitely large. All right, let's take a look at, this one is a little tricky. Let's erase the board. So here, take a look at that. We're on page 25. And I'm going to start fresh with this square root stuff. And I think I have a good way of explaining it. It goes back to our finding common denominators. I think that's a little easier than factoring. Some people like to factor. All right, let's take a look. Let's take a look. 8. We've got the limit as x approaches infinity of x over the square root of x squared plus 1. So this is a little tricky because we can't distribute this. We can't say, oh, that's just the square root of x squared plus the square root of 1. You can't. You can't distribute a square root over a plus or a minus. Remember, this is just that. So in the same way that when I had x plus 7 squared, I couldn't say that's x squared plus 49. It's not. It's x plus 7 times x plus 7. And so it's x squared plus 14x plus 49. You cannot distribute a power over a plus or a minus. What we can do is we can divide square roots by other square roots. So I can say, okay, I'm going to take the square root of x squared, which is just x, but I'm going to divide everything by that. So I'm going to say the limit as x approaches infinity of x over x, essentially, divided by the square root of x squared plus 1 over the square root of x squared. All right. Now, I can't write it underneath each thing. That's not correct, because then I, again, would have the square root of 1, and that's not okay. All right, so what we're doing now, that we can simplify. This is all under the guise of dividing everything by the largest thing in the denominator, all right? So because these are both under square root signs, I can write them all under the same roof, okay? like that. All right, now what I can do is I can split that into two different fractions. You know how when we had 1/3 plus, let's not make it 1/3, let's make it 1/13 plus 5/13. And then you could say that was like 1 plus 5 over 13, and then say 6/13. If this is allowed, where I can write it as two different fractions all under the same roof, I could also go the other way. I could go from there to there. That's what I'm going to do. So I'm going to say this is the square root of x squared over x squared plus 1 over x squared. I just kind of separated them out. Now I could do 1 here. So the limit as x approaches infinity of 1 over the square root of 1 plus 1 over x squared. Okie dokie. Everybody follow that logic? There's another way to do it where you look at this and you factor out square root of x squared. I don't like it. I think this way is, I know it's a little tedious, but I think it's easier to get your head around. So now the only thing going here is this going to 0. So we have 1 over the square root of 1 when we did the limit. And so that is 1 over 1, which is 1. And so we have a horizontal asymptote at okie dokie. So this is the limit is 1. I should have written it like this out, because that's where the last place I wrote the limit is 1 over 1, which is 1. Instead of working down. All right. Okay, let's look at number 9. That is a little tricky also. We're going to do the same kind of trick that we just did here. All right, so let's take a look. We've got x, the limit as x approaches infinity of x minus 7 over x squared plus 4 to the 1/3 power. Oof. All right, so we'll do a quick rewrite. Cube root of x squared plus 4. All right, so what we're going to do is we're going to divide the top and the bottom, that'll hit each term there, by the cube root of x squared. The cube root of x squared, the cube root of x squared. And then let's do a little fixin' here. So we have the limit as x approaches infinity of x to the first over x to the 2/3 minus 7 over x to the 2/3 over the cube root of x squared plus 4 over x squared, like that. Because they're both under the cube root sign, so I can put them all under the same thing. Just do one big long line there. All right. Now, 1 minus 2/3, that's negative 1/3. I think we're just going to leave that 7 over 2/3. X to the 2/3. And then this is, let's split that up. So we got x squared over x squared plus 4 over x squared. And so one more limit, and then we should be able to whammy it with the thing. So what do we got? We got x to the 1/3 to the negative 1/3, right? X to the negative 1/3 or x to the positive 1/3? Oh no, x to the positive 1/3. What am I doing? Negative. There's no negative there. It's positive because it was 3/3 minus 2/3. That's just 1/3. Whew, thank goodness we caught that. All right, so now what do we have? We have x to the 1/3 minus 7 over x to the 2/3 over the cube root of 1 plus 4 over x squared. All right, now let's go with infinity. This is going to go to 0. This is going to go to 0. The cube root of, this is what we end up with. We have x to the 1/3 over the cube root of 1, which is 1. And so now let's apply our limit. Let's go with the limit as x approaches infinity of x to the 1/3. Well, that is the cube root of infinity, but it keeps getting larger and larger and larger and larger. So that it's still going to go to infinity. So that means there is no horizontal asymptote. So again, basically at the end of the day, the bottom is 2/3 and the top is 1. 1 is bigger than 2/3. And so it's going to end up going to infinity. All right, let's look at the last one. What are they doing there? That's very much like, oh, I see. They have a negative there. It's negative infinity. So we're going to have to... This one is a real weird special case. So let's take a look at it. It's good that it's in your notes, but it's not going to land on a test or anything. So it's x approaches negative infinity, but... So we're going to divide by... square root of negative x squared, which when I do that, the square root and the squared, it's negative x. At the end of the day, it's negative x. It involves like imaginaries and things like that. We're not going to really go into that because we are approaching negative infinity. And so since they snuck this little negative on there, but it's going to be squared there. So a large negative number is going to still become positive. So to take a big picture look, we have to have this happen. So we're going to have the limit as x approaches negative infinity of x over negative x divided by the square root of x squared minus x over the square root of negative x squared. Like that. All right, and so now when we do this, we end up with the limit as x approaches negative infinity of -1 over the square root of x squared over negative x squared minus x over negative x squared. And so the limit as x approaches negative infinity is -1 over the square root of 1. So that's still 1 because the squared and it makes it positive. But then this is minus 1 over x. That's x over x squared, so minus 1 over x. But then we're going to infinity, so that becomes 0. We got -1 over the square root of 1, which is -1. And so we have a horizontal asymptote at y equals -1 for that one. So that is a trick. That's kind of a trick question. Okay, let's see. Number 1, if the degree of the numerator is the same as the degree of the denominator, the limit is the ratio of the coefficients of the highest powered terms in the numerator and denominator. We'll write that out. All right. So we're on the bottom of page 25. So the limit is the ratio of the coefficients. Remember, that's just fancy for the number in front of the variable. Of the highest power. Highest powered terms, also referred to as the lead coefficients, right? The leading coefficients are the big dogs in the numerator and the denominator. So we could say C number 5. Right, top of the page. You got x and x, it was 5/3. All right, number 2. If the degree of the numerator is larger than the degree of the denominator, then the limit is either positive infinity or negative infinity, and there is no horizontal asymptote. And again, we could say C number 7. And number 9, actually. And then number 3, if the degree of the numerator is smaller than the degree of the denominator, then the limit is 0. And there is a horizontal asymptote at y equals 0. Now, I've had students go, wait, Mr. Pledgey, wait. What if I'm approaching, what if it's 5 divided by negative 10,000, negative 100,000, negative 1 million? Well, 5 divided by negative 1 million is still negative 0.000000. It's still approaching 0. It's just approaching 0 from below instead of above. That's all. So there's still a horizontal asymptote at y equals 0. So unlike with number 2, where we do have to worry about the sign, if you have 4 times infinity, it's infinity. If you have negative 4 times infinity, it's negative infinity. And so you have to kind of keep track of that. But not so much with that one. All right. So let's take a look at what we have number 26. When working with transcendental functions, it is a good idea to be familiar with the graph. Some trig functions do not have infinite limits. Okay. So like the sine curve, they have y equals the sine of x. That's always bound just between negative 1 and 1, but it's not approaching anything. It just keeps bouncing between negative 1 and 1. So the top of page 26, they just have the sine curve. It just keeps going like this and this and this and this and this. It's not approaching anything. It's just always going up as high as 1 and down as low as negative 1. Whereas like the tangent curve, that has asymptotes all over the place, right? Everywhere where the cosine is 0, it's sine over cosine. So everywhere where the cosine is 0, that creates another asymptote. And so we have good approaching infinity all over the place with the tangent curve. Over and over again, periodically. All right, let's take a look at number 8. F of x equals ln x, the natural log of x. What's going on there? So we'll take a look at the graph of that and see if we can figure it out from the graph. So transcendental functions, natural logs are transcendental functions. So let's take a look at this. So the limit as x approaches infinity of ln x. And I know initially this does look like, oh, it's going towards something. It's not. This keeps going up and up and up and up and up. It keeps going. It doesn't approach. So it always gets higher and higher and higher and higher. That's infinity, positive infinity. It's going there kind of slowly, but it's going to keep going forever, up and up and up and up. What about the limit as x goes to negative infinity? Well, that's not going to work. It does not exist. You can't take the natural log of negative numbers. Okay, because remember what the log is. The natural log of x is equal to y, whatever. This is log base e of x equals y. So this is just a fancy way of writing an exponent. This is saying e to the y power is equal to x. Well, remember, that's 2.71 blah, blah, blah. All right, so 2.7 to what power will give me x? Well, that's fine. If that's 1, then it's 2.7. If that's 2, then it's 4 point whatever, 3, 4, and so on. You can figure it out. You're asking, e to what power gives me this number. That's what's going on there when you're doing the log. Well, you can't take something 2.7 to a power and end up with a negative number. You can't switch the sign. Just like we can't make it 0 either. I could get it really close to 0. I could put in y is negative 1 trillion. And that's 1 over 2 to the 1 trillionth power. That is so close to 0, but it isn't 0. And so we can't take that. You can't do the natural log of 0, and you can't do the natural log of negative 5, because there isn't anything that you can take a positive number to a power and make it 0 or make it negative. And so don't get that confused. I could take the natural log of 1 is 0. I can get y to be 0. I can put in 0, e to the 0 power. I can get that to be negative. I could say e to the negative 10. That's 1 over e to the 10th power. That is doable. That's going to be a decimal. But that's the x value. The x value can never be 0. The x value can never be negative. The y value can be zeros and negatives. All right. Okay, logs are fun. What about f of x equals e to the x? That's really just, at the end of the day, that's an exponential growth problem is all that is. It's just your base is 2.7 non-repeating decimal. So the limit as x approaches infinity of e to the x, that is infinity. And the limit as x approaches negative infinity of e to the x, that is 0. It's going to get ever closer to 0, but it won't actually ever hit 0 or cross it. So there's a horizontal asymptote at y equals 0. Because again, I can make it e to the negative 1,000. That is 1 over e to the 1,000th. Is really close to 0, but it's not 0. And it'll never be 0. All right. If you're asked to find horizontal asymptotes or end behavior of f of x, then the limit of x approaching infinity of f of x. Okay. Yeah, we're not going to sketch things. So skip the last one on 26 and the only one on 27. So skip those two. And then look at that. We're on 4.7. So that is it for 4.6. Hooray!